So, good afternoon to everyone. Welcome to section 13 on Combinatorics. This afternoon we have 4 talks. I'll be very brief with the introduction. I'm sure the speakers prefer to have time for them and not with introduction. Nevertheless, so let me say a few words about our first speaker, Balázs Szegedy. Balázs got his PhD in 2003 at Eötvös Loránd University in Budapest under Peter Palfi. Since then he has been at Microsoft Research Redmond and then at the Institute of Advanced Study in Princeton. And then he went to the University of Toronto, but now since 2013 he's back at the Rainy Institute in Budapest. Among of the many prizes that he has got, let me just mention in 2012 he got the Fulkerson Prize for his paper with Professor Laszlo Lovász on limits of sequences of dense graphs, and today he's in fact speaking about limits of discrete structures.
Thank you very much. So let me start with a very far-reaching story in mathematics that I really love. It started in 1936 when Erdős and Turán conjectured the following, that for every k and epsilon there is some natural number n, that for every subset in the first n natural numbers which has a density at least epsilon, there is a non-trivial k-term arithmetic progression. Now, roughly 20 years later, the case k equals 3 was solved using Fourier analytic methods by rote. And another 20 years passed, and then Szemerédi solved the full conjecture using combinatorial methods. A couple of years later, Fürstenberg found an analytic approach using measure-preserving systems. And let me tell you a little bit more about this. So he proved this Fürstenberg multiple recurrence theorem, which says that if you have a measure-preserving system, so you have a probability space and an invertible measure-preserving transformation, and you have a set of positive measure, then for every k and d, you can find an x in this set S, such that if you keep applying the transformation, then in every d steps, it comes back to the set for k minus 1 more times, which is quite similar to Szemerédi's theorem, and in fact it turns out to be equivalent. Fürstenberg has the so-called correspondence principle, which tells that this is equivalent with Szemerédi's theorem, and Fürstenberg thus gave a new analytic proof for this theorem. Now, okay, that will be tricky. So in 1998, Gowers found an extension of Fourier analysis, and this is called higher order Fourier analysis. And he could use this framework to give yet another proof for Szemerédi's theorem. And he could even give explicit bounds for how this n depends on k and epsilon. So already on this slide, you can see that this single conjecture generated 3 different approaches: the Fourier approach, the combinatorial approach, and the dynamical system approach. And story continues. All these approaches grew further and led to amazing development in mathematics. So the proof of Szemerédi's theorem leads to the famous Szemerédi's regularity lemma, which is a fundamental tool in combinatorics. Ergodic theory was also successfully applied to other hard problems in additive combinatorics, for which there is absolutely no combinatorial solution. For example, the polynomial version of Szemerédi's theorem, where the differences are assumed to be values of polynomials, and multidimensional versions of Szemerédi's theorem. And also there was a fantastic breakthrough in ergodic theory around 2000. The Host and Krah and independently Ziegler described certain characteristic factors of dynamical systems, And the description involves these geometric and algebraic structures called Nil manifolds. So quite interestingly, these topological structures arise in additive combinatorics, and I will tell you a little bit more about that later. Also, ideas from higher order Fourier analysis were used in the famous Green-Tao theorem on primes. And summary, this regularity lemma was also a crucial tool in the development of the so-called dense graph limit theory, which was started by Chase, Borg, Lovász, Sós, myself, and Westergombi. And this is an analytic approach to graph theory, which leads to new developments in extremal graph theory, property testing, probability theory, and so on. Okay, sorry about that. The hypergraph regularity method was developed around 2000 by Rödel, Skokan, Nagle, Schacht, and independently by Gowers. And in particular, this solves the so-called hypergraph removal problem, which again implies summary this theorem in a different way. And together with Gábor Elek, we had an analytic approach to hypergraph regularity method, which you cannot see on this slide already. But it continued, the story continues, and higher order Fourier analysis led to the algebraic theory of nilspaces, developed by Cameron and myself. It is rooted in the works of Host and Cross. So these objects, the nilspaces, are generalizations of Nil manifolds, but they also put Nil manifolds into a categorical setting. So you can study morphisms between Nil manifolds using the theory of nilspaces. So it's a new algebraic theory, and this was instrumental in formalizing higher order Fourier analysis as an algebraic theory. And essentially, my results imply that higher order Fourier analysis can be regarded as an algebraic theory which studies morphisms between these nilspaces. But nilspaces are also useful in ergodic theory. I will talk more about this, and also in topological dynamics. So this story looks very diverse. It has many directions, but there is a common theme in all of this I told you, and namely that we view structures in an asymptotic way. So this means that we focus on emergent properties of structures that appear when we look at them on the large scale. So in some sense, this is the physics of mathematics. In physics, you get used to looking at structures on the large scale, but so this provides an interesting mathematical framework for this. So this fits into this great program that finds the mathematics of large-scale behavior, which of course has many directions. But let me tell you a little bit more about this. So if you want to study the large-scale behavior of structures, it is more or less equivalent with studying structural limits. Why? This is because, take your favorite set of structures, for example, graphs, and graphs of different sizes may have similar large-scale behavior. And so that allows us, in an optimal case, we can express this similarity in terms of a metric. But the moment you have a metric, it leads to a limit theory because you can take Cauchy sequences in this similarity metric. And then, again, if you are lucky, limit points, I mean, not every limit point is in the set of familiar structures. You get new objects by taking the completion. And these new objects provide a very nice language for studying, very nice analytic language for studying the large-scale behavior of these structures. So now I come back to Fürstenberg. So Fürstenberg's approach to summary this theorem is a structural limit theory. It can be used to study the asymptotic properties of subsets in integer intervals as n goes to infinity. And the similarity between two subsets in intervals is given by certain pattern densities in the subset. I will come back to this later, but this is roughly the way how it goes. And limit objects in this metric can be expressed through dynamical system. This is basically Furstenberg's correspondence principle. And the asymptotic behavior of these subsets becomes precise in this limit, and that is the reason for this beautiful phenomenon that algebraic and geometric structures appear in the limit, such as compact abelian groups and Nil manifolds, which actually are already there in the combinatorial structure, but it's much harder to capture it because they exist only in an approximative way. But if you go to the limit, they appear as a precise structure, and you can do calculations with that precise structure. So ergodic theory is one of the first examples for an analytic theory that gives a powerful new point of view on discrete structures by expressing these asymptotic properties in the frame of a limit theory. Oh, this is bad because my lot is missing here. Anyways, so let me give you another example for how you can use similarity metrics. But now it is in the framework of graph theory. And so I need some preparation. For a bounded measurable function on the unit square, you can define this cut norm, which is the supremum of the absolute values of the integrals on product sets. And then let x denote the space of those two variable symmetric functions. They have to be symmetric, and also they have to take their values in the unit interval. And for two functions, we can introduce this similarity distance, where you take their difference in the cut norm, but you also look at all possible way of transforming the function u with a measure-preserving transformation. So here is the way how a measure-preserving transformation of the unit interval acts on two variable functions. Namely, it's just applying the measure-preserving transformation to the variables of the function, and then that way you can define this action. And so this distance becomes a pseudometric. It's not a metric. It can happen that two we call them graphons in graph limit theory, and it can happen that two such graphons have zero distance from each other. And so you can factor out by this equivalence relation where their distance is zero, and you get a metric space. You can represent graphs in this metric space. That's the nice thing. A finite graph has an adjacency matrix. Oh. Okay.
Refocus the
Okay, so has an adjacency matrix, and this adjacency matrix can be represented as a step function in the unit square with this formula. So every edge becomes a little block, a square block of ones. And here is the formula, how you represent graphs. And then you get a nice way of measuring the distance of graphs by taking just the delta square distance of their representing functions. Okay. Oh, this is looking very promising now. Thank you. So the main theorem in this regard is sorry?
By Lovash and yourself.
Yes, but will it disappear eventually, or?
Eventually, yes.
Eventually, okay. So Lovash and myself proved that this metric space is compact, and this implies two famous results, the Aldous-Hoover theorem on exchangeability, and which is a very important result in probability theory, but it also implies summary deregularity lemma even in the stronger form by Alon, Fisher, Krivelevich, and Szegedy. And I know that out of modesty, you should not put your own name in a lecture, but this is just almost my name because this is my brother, Mario Szegedy, so I can put the full name, at least in this case. So you can view this space X modeled out by this equivalence relation as a certain completion of the set of graphs, set of finite graphs. This is the playground of graph limit theory. And let me tell you a little bit more about graph limit theory. So this was a movement which started in the early 2000s. Benjamin and Schramm were interested in random walks on planar graphs, and they put that into a limiting context. They took limits, certain limits of bounded degree graphs, and they proved that random walks on these infinite versions return to the root with probability 1. Later, with Omer Angel, by the way, we generalized this result to excluded minor families. But so this is very complicated. Another development was done by Friedman, Lovász, and Scriver. They brought the notion of reflection positivity into graph theory. And this was crucial in the development of graph limit theory, by the way. Various extensions were defined by Bolobás, Riordan, but later many other works, I cannot even mention all the follow-up works by, for example, Jaroslav Nesetril, Patrice Osodana de Mendez. Also, Razborov has his flag algebra method, which is very much related to this framework, and I could list forever. I mean, there many people participate in this. But one of the main challenges in graph limit theory is that depending on the number of edges, there are different useful limit notions. Because in dense graph limit theory, if the graphs are too sparse, then they trivialize in the limits. So for sparser graphs, you need different limit notions. And one of the main challenges is to find a coherent picture. And this is work in progress. So some more interesting limit theories. This is one of my favorites, the local global limit theory for bounded degree graphs. The notion itself, the metric was introduced by Bolobás and Riordan, and later with Hatami, Lovász, and myself, we proved the existence of the limit objects, which are graphings, so-called Borel graphs with special properties. And it turns out that this is a very useful limit theory. This was crucial in my proof of together with Agnes Backhaus, we verified this Berry conjecture for random regular graph that this morning Nalini mentioned in her inspiring talk. So this result actually required very heavy graph limit theory. So this shows, even with graph limit theory is complicated, but without graph limit theory it would be impossible to do this, or it would be much more complicated. So it shows the power of graph limit theory already. So there is a limit theory for hypergraphs, and it actually led to the development of the so-called ultra-limit method. This is in a work by Gábor Elek and myself. There is a really interesting direction which studies limits of permutations by Hoppen, Koayakawa, Moreira, Rath, and Champagnot. And last but not least, there is a limit theory for subsets in abelian groups. I started this limit theory, and this will come back in my talk. It will have an important role. So, the question that we can address, is there a limit theory for additive or arithmetic combinatorics? So the famous correspondence principle by Furstenberg allows us to view ergodic theory of z actions also as a limit theory for ordered 0-1 sequences. And think about it. If you have a subset in an integer interval, you can just take the characteristic function of this subset, which is represented by a 0-1 sequence. So if you take limits of subsets in intervals, it's the same as taking limits of longer and longer 0-1 sequences. And in that case, you can define convergence or similarity. So two sequences are similar if small patterns like 0-0-1 or 0-1-0 have similar frequencies. And in the similarity metric, you give less and less weight to the similarity of longer and longer sequences. You can metrize that. And you get a nice limit notion, which says that a sequence of 0-1 sequences is convergent if the density of every fixed pattern converges. And the completion of 0-1 sequences in this metric can be always described as a shift invariant Borel measure on the Cantor set 0-1 to the z. So this is how dynamics comes into the picture, because there is this shift which preserves this measure. And here is an interesting observation that Benjamin-Isham limit theory of colored bounded degree graphs actually generalized this Furstenberg's framework, because if you want, you can represent these 0-1 sequences by just longer and longer passes, which are very simple graphs. And you color the vertices of these longer and longer passes by 0 or 1. So you have colored graphs. And then you can take the limits of these colored graphs. Now, the Benjamin-Isham framework generalizes that, and you get similar dynamical kind of looking objects, which I don't have time to explain. But so this Furstenberg approach is related to sparse graph limits in some sense. It's very interesting that the Gauers' approach, which is this Fourier analytic approach, is a completely dual view on additive combinatorics. It's a dense, it's more related to dense graph limit theory or limits of dense structures. And that actually explains the difference between the two directions. So let me again return to this history of Gauers' proof. So in 1998, Gauers gave this new proof of Sobre-Eddy's theorem, and a crucial tool in this proof is the introduction of these Gauers uniformity norms for functions on abelian groups. And he coined the name higher order Fourier analysis for this method. And the beautiful observation by Gauers is that if you have a function on an abelian group, then the U2 norm, the property that the U2 norm is separated from 0 somehow, is equivalent with the fact that f has a non-negligible correlation with a wave, which is, in this case, on an abelian group, is a linear character. So this inspires the following question. What about the higher Gauers norms, UK? What do they tell you about the function f? What are higher order waves? We want to say something like the U3 norm, for example, is non-negligible if f correlates with a quadratic wave, whatever it means. The question was left open by Gauers what these higher order waves are. Nevertheless, he could use the norms to improve on Sobre-Eddy's theorem, the bounds in Sobre-Eddy's theorem. So for this reason, Gauers' work started this line of research to understand higher order waves. And there are long and deep works by Green, Tao, and Ziegler. And I have an alternative approach, which was done simultaneously. But my approach is totally different. Although there is, in terms of results, there is a considerable intersection. So in my approach, higher order waves are basically just morphisms from abelian groups to Nil manifolds, or more generally to Nil spaces that we introduced with Camarena. And to give you a little bit more explanation for this, linear characters themselves are homomorphisms into the circle. The circle is embedded into the complex plane. As a multiplicative structure, it's a group, the complex unit circle. And linear characters on abelian groups are just homomorphisms into the complex unit circle. Now, higher order Fourier analysis provides an extension of this in terms of homomorphism. You have to, in order to understand the Gowers norms, you actually have to study homomorphisms into these fantastic objects called nil manifolds, which are geometric, topological, and algebraic structures at the same times. They are obtained from nilpotent Lie groups by factoring them out by a co-compact lattice, and you get a compact manifold, just as the circle is a compact manifold. You get more general compact manifolds, and these are the nil manifolds. Yeah. So let me address the main question of this talk. I mentioned these different directions in summary, this theorem, these different approaches, the ergodic approach, the higher order Fourier analytic approach, and so on. And it seems that the same structures show up in these different approaches. So it suggests that there may be some unification between the ergodic theory direction and the higher order Fourier analysis direction. What connects these subjects. And this was kind of a missing part of the puzzle. And in this talk, I try to give you some partial answer to this. So this will be joint work with Pablo Candela. But I need the notion of exchangeability to describe our approach to this question. So exchangeability is a subject in probability which studies joint distributions of random variables that are symmetric, that are preserved by certain symmetries. So the simplest and probably most famous example for this is when you have countably many random variables, and the joint you require that the joint distribution is invariant under all permutation of these variables. And the famous definite theorem says that this can only happen if this is a mixture of IID distributions. So in particular, the ergodic ones are just IID distributions. Aldous and Hoover Theorem is a generalization of this. Here, random variables are indexed by pairs of natural numbers, say unordered pairs, and still the symmetric group acts on the natural numbers, and this gives a different action. This has fewer symmetries, and you can still give a characterization for such exchangeable systems. By the way, in this subject, symmetry can mean also partial symmetries. You don't have to require some global symmetry which shuffles the random variables. You can say that these 10 random variables have the same marginal distribution as these 10 random variables. This is what I call a partial symmetry. And another nice example for exchangeability was proved by Nikos Frantzikinakis, who studied random variables indexed by integers, and the symmetries are the shifts. And also, you require that when you multiply every natural number by some fixed number k, then you get the same, that marginal. If you take just every case of this random variable, then you get the same distribution. This is a very deep result, by the way. It uses the works of Host and Krah. So this is very complicated and deep result. So exchangeability theory is hard in general. It's hard in the sense that we know only very, very few examples where we can really describe this. I mean, the proof of definite theorem itself is not hard. The Aldous Hoover is already harder. This Frantzikinakis result is very, very hard. And in general, we know almost nothing beyond this. So very few things are known. But also, it turns out that those few cases that are known, by the way, I also should have mentioned Kallenberg, who has also an extension of Aldous Hoover result. But so it's very hard, but those cases which are known turn out to be very useful. So it's worthwhile. It's really interesting to prove new theorems like this. By the way, the Aldous Hoover theorem is closely related to graph theory and graph limit theory, as it was pointed out by many authors. There is a nice correspondence between them. And so here is the question. Is there an exchangeability problem which is related to additive and arithmetic combinatorics? Well, not very surprisingly. First of all, there are quite a few, and not very surprisingly, because you want to understand arithmetic combinatorics, you need the arithmetic groups. So here I show you 3 such exchangeability problems. So first of all, assume that your random variables are indexed by the infinite dimensional lattice z to the infinity. And there is a natural action on this lattice of GL infinity z. And so we can ask what are the systems of random variables like this that are invariant, where the joint distribution is invariant under this group. Well, this is looks a bit hard because it's not even transitive, this action. There are orbits. The 0 itself is in a separate orbit. So maybe a somewhat simpler question is to enlarge the group a little bit and include all the shifts. So this becomes a semi-direct product. And then again, the question arises, the same question. And then finally, there is a local version of this, which we call cubic exchangeability with Pablo Candela, affine cubic exchangeability, and this focuses on just to the 0, 1 to the infinity cube. So you look at the inherited symmetries from this problem too on the cube, which can be described in a very nice way. So this tells you that the marginal distributions on affine cubes of the same dimensions are always the same. So this is a good example for partial symmetries. And let me just tell you some connections to additive combinatorics. It is, in fact, directly connected. So let A be a fixed abelian group. Even Z2 is interesting in this case. And let S be a subset in A. And then take the homomorphism set from Z to the infinity to A. Oh, by the way, since A is finite, this homomorphism set is a compact topological group, so there is a Haar measure, and thus we can talk about random homomorphisms. So if you compose these random homomorphisms with the characteristic function of S, which means that for every element in Z to the infinity, you get a random variable. You send it somewhere to a random place, and then you evaluate this function, which means that this is a random variable, and this gives you a joint distribution. And this joint distribution is easy to see that it's invariant under GL infinity Z. And so, by the way, this way you can encode functions on abelian groups into exchangeable systems, into these affine exchangeable systems. If you take, instead of homomorphisms, you take affine homomorphisms where you can compose a homomorphism with a shift, then you get this second case, you get an exchangeability like in problem 2. So, but this, the fantastic thing is that if you have two different abelian groups and subsets in them, you can still compare them because both produce some exchangeable systems, and exchangeable systems are in the same space. You can compare them with using the weak topology. You can study convergence. So this gives you an approach to a limit theory for subsets in abelian groups. Now, the good news is that we could solve the third problem. And we proved that every ergodic affine cubic exchangeable system comes from a so-called nilspace. I don't give you the details, but it's a similar construction that I just explained in the case of abelian groups. So this is an informal version of the statement. But here you have to switch to nilspaces. And for every nilspace, so it's an if and only if, so this is an exact characterization of these exchangeable systems, which is a good advertisement for probabilists of nilspaces that they come up naturally in probability theory. If you formulate the right exchangeability question, then the nilspaces are the right construction to look at. In fact, so this is related to arithmetic groups. So ergodic measures form a closed set. By the way, if you understand ergodic measures, then you understand everything, because everything is composed of ergodic measures. So that's why I just formulated it for ergodic measures. Proof is very long, but about 30 pages deals with some groundwork in probability theory that we didn't find anywhere. It's some theory, general theory of couplings of probability spaces, and this should be well known, but somehow we didn't find. But the difficulty is the following. How to extract geometric structures, such as Nil manifolds, from probabilistic structures. An exchangeable system has absolutely no topology. It's just some joint distribution. And you want to extract finite dimensional manifolds in some ways. And the ideas that we use is related to one of my joint papers with Laci Lovász, the regularity partitions and the topology of graphons, where we introduced topological versions of graphons. We introduced a way of putting a unique topology on graph limits, and that allows you to study extremal problems in graph theory using topology. But this point of view was also useful here, and it leads to this theorem. So now, to continue, I need to explain the beautiful work of Host and Krah a little bit more in ergodic theory. So, in ergodic theory, people study measure-preserving systems, and already in the general setting, groups are acting on measure spaces. But the question of Z actions is already very interesting and non-trivial. People spend decades with just that case. And so we try to understand the Z actions on measure spaces. And for every natural number k, Host and Krah introduced a uniformity seminorm on the function space, L-infinity function space on omega. And these norms, by the way, are closely connected to Gauer's norms. And for each Host-Krah seminorm, there is a beautiful correspondence between these seminorms and certain sigma algebras, where bk is again Z invariant, so it's a factor system, and it has the property that the projection to bk, sorry, this is a typo, it's the same B. So the projection to bk is 0 if and only if this seminorm is 0, which means that, in fact, uk plus 1 is a norm on L infinity of this factor. And if k equals to 1, then this factor is the so-called Kronecker factor, which has the structure of a compact abelian group with a given shift. It's a classical thing used in ergodic theory. But it turns out that bk is crucial, the general understanding of bk is crucial for many problems in additive combinatorics. In particular, the B1 factor is responsible for the 3-term arithmetic progression case to understand the 3-term arithmetic progressions, and the bk factor is responsible for understanding the k plus 2-term arithmetic progressions. And so the famous Host-Krah theorem gives a geometric characterization of the factors bk. The measure-preserving system, if you restrict it to these factors, is the inverse limit of Nil systems. So a Nil system is the following. We take a nilpotent Lie group, a co-compact subgroup, and then we take this Nil manifold, which is the left coset space according to gamma. And N, so N is a finite dimensional compact manifold, and L, the Lie group, acts on it. It has this Haar measure, and which is preserved by L. And the Nil system is the action of a given element of a cyclic subgroup from L on N, and ergodicity is assumed. So this is a Nil system. And so these Host-Krah factors are inverse limits of such systems. That's the famous theorem. Again, the proof is very long. It's roughly 100 pages long. But it was proved in a paper by Berger, Zontao, and Ziegler that Host-Krah seminorms can be generalized to other abelian actions, and furthermore, it was mentioned in the same paper that probably they can be even generalized to nilpotent actions. And they analyzed the special case of Zp to the infinity, where our abelian group is just this group. And so even that led to interesting cases for the inverse theorem for the Gauss norms. But many people asked for a general description of these host-Kra factors. And this is what we did with Candela. And it turns out that characteristic factors of the host-Kra seminorms for countably nilpotent group actions are so-called nilspace systems. So this is implied by our results on exchangeability. So nilspace systems are slight generalizations of nil systems. But if you also assume that the group is finitely generated, then we actually obtain a direct generalization of the host-Kra theorem, namely that these are just inverse limits of nil systems. So these theorems generalize the celebrated host-Kra and also the Ziegler results for Z actions, from Z actions to arbitrary nilpotent actions. But in particular, this gives a new proof also for this host-Kra-Ziegler theorem. Sorry?
What's the difference between these two theorems? One is a
nil space systems, the other is a nil system. So the nil space system is a slight generalization of a nil system, where the inverse limit is, so you have certain actions on these new objects called nil spaces, and then you have to take inverse limits of them. This is different. This is not exactly the same, although they have an algebraic theory now. And by the way, I just mentioned that in this paper we have to use a variant of the previous exchangeability theorem. We need certain versions of these cubic exchangeable systems which satisfy certain conditional independence properties. It looks technical, but it seems that this is a very good notion that we use in our paper. So this is just some interesting technicality. So back to additive limit theory. How does this contribute to the limit theory for functions on abelian groups? So let me give you a little bit background. If you have a function on an abelian group, then you can study densities of linear configurations in these abelian groups by this formula. I don't have too much time to explain it. But this is just the density of the three-term arithmetic progression. And you may ask if you have a sequence of functions on different abelian groups such that the density of each such density converges, then what is the limit object? So this is basically a way of formulating these limit theories in the additive framework. And I have to skip here certain details. But in fact, our results with Pablo Candela imply that the limit object, at least in the special case when the linear combination is given by 0-1 matrices, at least in these cases we can describe that the limit objects are functions or nil spaces. I mean, for abelian group, this was already there in my earlier work, but our current results give a refinement of this limit theory where we can take limits even where the functions are already defined on nil manifolds or nil spaces, and you can start with such functions. So it gives a slight extension of that. And so I also have to give you some interesting open problem to think about. This is something that I really like. Take just the group SL3Z. And take the set omega, which is just the set of triples where the greatest common divisor is 1, and G acts on omega. And can you describe the related exchangeability problem? So two things may help. G has Kazhdan property T, so which implies that by a theorem of Glasner and Weiss, ergodic measures are closed, which gives a hope that actually there is a characterization. And new results in arithmetic exchangeability suggest that characterization is not completely out of reach. But here is my last slide, which actually rounds this story. Make this story round, that I promised you some unification between the ergodic direction and the higher order Fourier analysis direction. And it turns out that this exchangeability theory, if you use it as a black box, this actually is also helpful in proving the inverse theorem for the Gowers norms. In fact, it can be used to give a rather simple, relatively simple proof for the inverse theorem, and it can be also, if you use it as a black box, it gives you a rather simple proof for the famous Hoskra-Ziegler theorem. So the black box is enormously complicated. As I said, it's hundreds of pages long. But this black box gives you a common root for the difficulties in higher order Fourier analysis and in ergodic theory somehow. And so this is a partial answer to the question whether you can unify these two different looking, but of course these two directions share many similarities, they look different, and this is how we approached it. So I think I finish here.
Thank you very much, Balázs. So questions? So, second attempt, questions?
Seems that I answered all the questions already, so.
Okay, I would like to ask one question. So, at the very beginning of your talk, you said that some of the objects that you have that are much cleaner in the limit do manifest themselves in the combinatorial context. Could you give one example which wouldn't be so nasty?
Yes. So there is a concrete formula on cyclic groups. Unfortunately, I have to record this formula, but involving some very simple fractional parts. You can write up a function, and it looks really elementary. But it turns out that if you want to understand the limiting behavior of this sequence of functions on just really cyclic groups, which are the simplest things on Earth, then the limit object is a function on the Heisenberg-Neal manifold. So the fantastic thing is that non-commutative structures come into the picture when you take the limits of commutative structures. This is the most fascinating thing for me. And so this is a very, very concrete example. But also in graph limit theory, there are examples where certain compact topological groups appear in the limit, and so on. So there are various examples.
Okay, so if there are no more questions, then thank you very much to Balázs.